Huh. Okay, yeah, that's, but it's sort of counterintuitive. Well, okay, it's not counterintuitive, but it's non-trivial that you get, I mean, yeah, you of course get it. So the identity gives 3. So I have 1 by 6 times 3 for the identity permutation, right? It has 3 fixed points. There are 3 permutations which have 1 fixed point. So 3 times 1, so which is 1. And there are 2 derangements, so it's exactly 1. But what is more is true is that the variance of this quantity is also 1. So not only is the average value 1, the variance is also 1. And something even wilder is true. The first n moments of f are the same as the moments as those of the Poisson distribution with mean 1. So so Tulsi knows a proof, so we can discuss it in the discussion section. So it agrees with the Poisson distribution exactly up to n moments, and then it varies. So on Sn, it follows.
The number of fixed points like that distribution goes to Poisson, right? Because n goes to infinity or something like that.
Is that right?
That's well known. I mean, Xavier.
Okay.
But this is like.
So Tulsi claims a very easy proof, so we'll see it. Yeah, so I'm sure you know how to prove it. Yeah.
If lambda is less than Cn for every I, that's enough for you. I mean, that's more than enough for you, right? Let's say C is 0.9, whatever you want. All the typical partition won't have something less than just 0.9. This is the basic quotient theorem.
Right. It's like root n, yeah. Lambda 1 will be like root n.
So here you are asking if all the lambdas are less than, say, half n, that's more than enough for you, or 0.9 n.
Yeah.
That satisfies this condition. So you can just pull it off there.
So, but then how much am I missing? One has to sit and calculate, no?
There is like theorem comes with a last deviation. It's exponential in minus n.
Okay.
So there is some confusion because your k in this calculation you don't require k to be 1 n log n. So you have to do that.
K.
If you use this bound, why 1 times n log n is not clear? Why not half n log n or something? That has to be checked.
Right. Yeah. Oh, so it's not, no, isn't it clear?
So this c to the 2k n factorial. N factorial is e to the n log n.
Yes.
And
E to the, yes. E to the
it
n.
has to be a very specific c for each two.
E to the n log n minus n. And oh, by the way, this c has nothing to do with the k equals, okay, so maybe I should say c prime. I mean, this has nothing to do with k is n log n plus cn. That c has nothing to do with this. Yeah, so I mean, here you're right. I mean, we don't get something strong. I mean, as I said, I mean, I'm not sort of gone. I mean, I haven't seen anything stronger written than this. Okay, so in the last 10 minutes, maybe I'll just give you the idea. So you know the expectation of u under the uniform distribution of this f pi, and we know the variance. We are going to compute the expectation under q star k of this quantity and the variance under. So then we'll be able to say something. So so here's where the defining representation comes. So want to compute expectation under q star k of f. right? So this is the first step. So consider the defining representation of Sn. So pi goes to rho of pi, which is rho, which is the permutation matrix of pi. So remember, what I want is the number of fixed points of pi. So in terms of the permutation matrix, what is it? It's the trace, right? So f of pi is trace of rho of pi. Okay, but now using the fact that the defining representation, which Murli proved maybe in the first class, the defining representation splits as the trivial plus the standard representation. So this splits as the representation corresponding to n plus n minus 1, 1. So expectation under q star k of f is the sum over pi in Sn of trace of rho of pi, q star k of pi, and this is the trace. So you get a block diagonal decomposition with a 1 here, a 1 by 1 matrix over here, and I have a q star k of n minus 1, 1. For this partition, we already calculated how q star k looks like, right? That was the first term over there. So this is exactly 1 plus n minus 2 times 1 minus 1 by n to the k. Okay? And when k is n log n plus cn, this is 1 plus e to the minus c, 1 plus big O of 1 by n, which is bounded away from 0 when c is less than 0. So we want to get the lower bound, right? So we are saying that if you go less than n log n steps, then you are going to be something away from 0. There's a 1 plus something which is small, so you know you're going to be away from 0. But unlike the old approach where we looked at some subset of Sn and we computed its probability under these two distributions, here we are looking at a random variable. So just because we have control on the mean is not enough to say that the distance between them is going to be small. So we actually need the variance also. And here is where we'll need the tensor product. So since I just have 5 minutes, I won't give more details. I mean, I won't give too many details. So this is, just let me remark that this is not enough to bound dTV of q star k and u. Need a second moment. We need some control on the second moment. So to compute the variance, var under q star k of f, we need a formula for trace of rho of pi squared, and this comes using a tensor product of so I don't know, fact. So using the tensor, using tensor product of defining, we get trace of rho pi squared is 2 plus 3, the character of n minus 1, 1 at pi, plus character at n minus 2, 2 at pi, plus character at n minus 2, 1, 1 at pi. I have no idea how to prove, absolutely no idea how to prove such a thing. Okay, but this, so we are not quite done, there's quite a bit of work, but let me just tell you the steps. So the steps now, what one would do, so compute expectation of under q star k of f squared using the formula. Okay, this is equal to, this guy over here is equal to 2 plus 3 times n minus 2, 1 minus 1 by n to the k. So each term comes from one of those expansions of the over there, plus n minus 1, n minus 4 by 2, 1 minus 2 by n to the k, plus n minus 2, 1 by n to the k, plus n minus 2, n minus 3 by 2, 1 minus 2 by n to the k, plus n minus 2 times minus 1 by n to the k. Now, the variance is the expectation of the square minus square of the expectation. So compute the variance of q star f and show that when k equals n log n plus cn, this is 1 plus e to the minus c, 1 plus big O of 1 by n. And last step is to use the Chebyshev inequality. So if you have control on both the first and the second moments, or the mean and the variance, one can use Chebyshev. Use Chebyshev's inequality. Let me state it in this case. Q star k of the following event, the set of all pi, such that the distance between f of pi and the expectation of q star k of f, expectation in q star k of f is greater than a times the square root of variance of q star k of f. If this has probability 1 by a squared. Okay, so then this to show, use this inequality to show that if minus c is large, then q star k is supported so this thing supported on e to the minus c plus or minus a e to the minus c by 2 with probability 1 by a squared. Then you use the Chebyshev for the uniform distribution, and you show, you show some estimates and you get it. Okay. and also use Chebyshev for uniform and show that TV distance between Q star K and U is bounded away from 0. Okay, so this completes the proof. Okay, so I've skipped lots of details, but you can see it's a nice mixture of ideas from representation theory and probability.
What is the estimate for what is B, that constant? Is that or not?
No, there's. I don't know any clean expression for B. Yeah. They just need that you're not getting close to the uniform distribution if K is less than n log n. Yeah. So as I said, lots of things are sort of unsatisfactory about this in the sense that they are not. I don't know how to do them cleanly, but I think the experts believe that, as Manjunath pointed out, that one should be able to do them using ideas from Vashik-Kerov and maybe further results. And people simply don't believe that it's worth the effort to write these all things down. So nobody has done it carefully. Okay. I have to give 2 more lectures.